This is the Banana Data Podcast, a podcast hosted by Dataiku. I'm Triveni.
And I'm Chris.
And together, we'll discuss the good, the great, and the ugly of AI. Today, we're talking about the most common misconceptions in AI and the mistakes that plague most data scientists as a result. So, Chris, this is your second episode with us, and I think listeners want to get to know you a little bit more. So tell us one of your pet peeves.
You know, when you open the door for someone and let them in and they don't say thank you, that really just grinds my gears.
Okay, well, I meant your pet peeves in the machine learning data science space.
Oh, there's a lot of those too.
Yeah, I have a lot too. So I thought it'd be fun to dig into those today. There's, I think, a variety of pet peeves on the scale, from the little things of, did you do 4 spaces for your tab, or did you hit the tab button, to, much bigger questions. So I wanted to kick it to you and see what really gets you going in terms of a pet peeve.
Well, besides the small things like not showing the entire y-axis or using pie charts, which I think breaks everybody's hearts in the data space. There's some bigger concepts like this perception that more data is always better. And no matter what, the more observations you have, the better you're going to be as a machine learning engineer, and so on and so forth. I hate that perspective because I don't think that that's true.
Yeah, I would totally agree. I think there's this perception or belief that if I just give the machine, right, or the computer 1 million data points, out will come this amazing model on the other side because it had 1 million data points to learn from. But if 95% of those data points are noise or not useful or just pure garbage, what you're going to get is not very good on the other side. And so more is not always better in this case.
So then what do you think is better?
I think that there's a risk of using this data that's not very well collected or actually filled out. You might have a lot of missing values. You might have categories or values that were put into your database 10 years ago, and now those same ideas or categories or elements don't exist anymore. If you're using outdated data, if you're using a lot of missing data, what's the point then of having more of it? I would rather have a small set of data, not too small, right? 10 records isn't going to do me any good. But I'd rather have a smaller set of data that is well curated. We know where it came from. We know how it was collected. We know that it is accurately representing the population that we're trying to work with.
Yeah, the more data you have, the more prone you are to, like you mentioned, having missing values or having irrelevant values or incomplete values or even relics that are no longer important. And the more that you have of that, the more the data scientist has to do to overcome that. And some of this imputation or filling in those missing values really is just smoothing over an issue, oftentimes putting a Band-Aid over a wound. There is a place and time for that, but if the proportion of your data set is missing is quite high, then you're not really doing yourself a service at all. You're actually doing yourself a very big disservice and tricking yourself into thinking, hey, I've got 1 million records, this is great. But a lot of those records are not really going to give you any value.
Yeah, no, I think that's totally fair, especially when you think about the process of data cleaning and having to come up with all of these things to fill in the missing and all that. I don't really want to deal with cleaning data over 1 million records. But I do think also that the idea of how useful the size of your data is can function on a bell curve, because you need a minimum amount to actually do something, right? To actually do machine learning. If I have 100 records, but 300 columns, I'm not going to get anything out of that. So there is a minimum amount that makes sense for your project. But then after a certain point, you're not really getting any return on value because you're just using unnecessary data.
Maybe one of the reasons why this comes up quite a bit is that to understand what is not enough or too much is a very ambiguous question. And it often depends on the question you're trying to answering, the kind of data you're mining, and nobody will ever really have a hardcore, yes, this is the correct number of observations you need for certain things that are typical in the data science space. So I think we try to protect ourselves, or there's this vision of protecting yourself by just gathering more and more data. But this garbage in, garbage out concept you already mentioned is to keep at the forefront of our mind.
Yeah, and I think actually it's interesting because now you're seeing In some very specific cases, machine learning algorithms that can help drive how much information it needs to be able to make a better prediction. So I'm thinking about active learning and labeling data. So I think a big problem in a lot of industries in a lot of places is that there's all this great data, but it's not actually labeled for us to know what classification to put it in. So you can imagine like somebody's gone out and collected tens of thousands of pictures of different kinds of like items, paper boxes and cans and bottles and all these things.
What kind of pictures are you taking, Triveni?
I just take pictures of trash. It's just like it's like my hobby. So someone's taking a bunch of pictures of random objects and has some of the data labeled to say, okay, this is paper, so it can be recycled. This is a metal can, it can be recycled. This is just garbage. Don't recycle this, right? And if I have a million pictures like this, I do not want to spend that time to label it all. So I can use active learning to actually have the machine learning algorithm say, all right, you've given me a certain number of cases, right? So like maybe you've given me 10,000 labeled points. Based on that, I can look to the other images in this data set and say, okay, I think I'm going to get the most information from you labeling these specific images. And now instead of labeling 1 million images, of which maybe only 5% are useful, the machine learning algorithm itself is saying, I need you to like label these specific images because that's going to be more useful to me. I have enough examples of what cardboard is. Don't label any more cardboard for me. I need to know more examples of metal. And you haven't given me enough of that. So go label some of these pictures, please.
And that's also, again, having the human in the loop element. So the human being is actually helping to train the model. It's not necessarily the amount of data that you've provided the model, but the golden nuggets of information that the human is providing to guide the model that's really being the force behind the learning.
Yeah, exactly. Right. And so if you just throw a big data set at an algorithm, but assume that once I've thrown that off, I'm washing my hands of it and I can just let the algorithm do its own thing, then you're setting yourself up for a potentially very poor model because you haven't even like paid attention to what's in your data, let alone what's coming out.
Well, I do hope you wash your hands of the data after dealing with all this garbage, Triveni.
Listen, gotta keep it clean. Gotta keep it clean. It's a very curious problem because there's a lot of technology now oriented towards processing big data. You have Hadoop, you have Spark, you have all these big data storage warehouses. So yes, big enterprises have lots of data. They have to figure out how to store it and use it and manipulate it. Does that always mean that they're doing the right thing? I don't know. And I think it's a pet peeve to assume that they are.
We could talk about pet peeves and things that annoy us all day.
All day or day.
And now it's time for the part of our show where we discuss complex data science topics in simple terms. So, Triveni, can you describe the AUC and ROC curve in English, please?
The AUC ROC is a metric used in classification models to tell us how well our model is doing at predicting new data. And it often is seen as a gold standard because it balances between both the true and false positive rates that one expects in a classification model.
Well, thanks for explaining that in English. So yeah, the reason why I wanted to bring that up is because that's also another pet peeve of mine. I know you kind of mentioned that the AUC ROC metric is good for balancing false positives versus true positives. And those are very important, especially in a classification problem, but it's not the end all be all. And I think particularly in the case where the cost of making a certain type of error in a classification problem is not the same.
Oh, yeah. And that's, I think, the critical point here. The AUC ROC, which everyone's always chasing, is actually masking a lot of potential error in your model. Like I said, it's balancing for both true positive and false positives.
So what's a case where you might not want to use the AUC?
So I think a really common example is actually in cancer detection models. You might have a set of data points about people who get some kind of cancer, but it's actually a very imbalanced data set. Of all the cases, maybe only 5% have cancer. So if I were to build a model to predict the likelihood of cancer, well, my AUC ROC actually might be quite high because the machine learning model is getting all of the negative cases correct, but missing out on all the positive cases. And even though it's missing or guessing incorrectly the positive cases, that only makes up 5% of the full data. So at a high level, the model says, I'm doing great because 95% of these cases were negative, and I said that, even though the other 5% got inaccurately tagged. And especially in something like cancer detection, I don't want my model to give me a false negative. I don't want to be told like you're free and clear and then actually not. And so I think in those kind of cases, you need to look to what are you actually trying to do with your model, or what are you really trying to predict, and then use the right metric for that versus something that's just a scale invariant metric.
Yeah, I mean, you can get into this problem where you can publish an article or have splashed across the New York Times, machine learning model is 95% accurate in predicting cancer, but that's not telling the whole story. And really, your model is just terrible and it's just predicting no cancer for everybody, but in actuality, that's not useful for anybody.
Yeah, and I think because we're dealing with data that's often very messy and imbalanced, even if it's big, even if it's small data, we have to come up with other ways to understand how well we're doing based on that data and assuming that that data is actually representative of the population we're dealing with. So what are some methods you use, Chris, to sort of rebalance?
So in cases like this, I think it's important to evaluate the cost of making these different types of errors. So if we go back to the cancer example, the two types of errors we can make are claiming that somebody has cancer when they really don't, or missing that somebody has cancer and claiming that they don't have cancer. So there's different impacts and penalties to those types of errors. I think one way we get around this is assessing what those costs are and then coding that in our analysis. So maybe it's 5 times worse to make this type of error than that type of error, and I include that penalty in my algorithm.
And that requires the data scientist or the folks involved to be aware of what kind of impact they want to make with their model and what kind of impact they could potentially make in a negative or positive way if they're not paying attention. And so if you just say, well, I'm going to build a model to predict cancer, I got it 95% right most of the time, great. But that's not actually showing a reflection on what you're building and how it's actually being used or how it's actually affecting the world around us as a result. I think that's for me where like the pet peeve really hits, because the sort of blind reliance on this metric is the one that we all follow and every other metric is like silly and not important, right? That's where I get annoyed, because there is no one size fits all solution in data science. And we all know that. And so why are we giving so much importance to a single metric for it?
Yeah, there's a bridge in between the domain knowledge and the technical knowledge here. And maybe talking to practitioners in the medical space, or talking to whatever it is, economics, so on and so forth. That's really going to be the missing element here, not just putting all the faith in the numbers.
You know, as we're talking about these pet peeves, I think I'm starting to see the underlying issue is that we tend to think in very dogmatic ways about what is good ML, what is bad ML. We say you should have more data. You should have a really high ROC AUC. You should be able to deploy it over 10,000 GPUs that are each sized at 500 gigabytes. And this misconception that the more complicated things are, the more high tech, the more intense things are, it's correct. But there are gray areas in this.
Yeah, and gray areas make people uncomfortable. And it's so much easier for us to lay these hard lines and say, this is right, this is wrong, so on and so forth. But as everything in life, but very often in data science, there's ambiguity. And we've got to be comfortable with being uncomfortable.
Yeah, and I think like because we're dealing with numbers and data and these things that are seen as very scientific and technical, we expect that our approach should be equally methodological and scientific, which in some cases, yes, right? Like you should look at your data, you should clean your data, whatever. But should you always stick to the same metrics? Should you always stick to the same methods or even data sources every time? No, because what you're going to be doing is going to be different every time. And what you're trying to get out of the algorithm or the process or the pipeline isn't going to be the same, let alone across industries, across companies. Even for your own projects, you're going to have different things that you need to be attaining. And it's not always going to be the same thing over and over again. Because if it was, I don't think a lot of us would be data scientists.
So you're telling me I shouldn't just ask you for the answer all the time?
Yeah, no, I know you're always trying to cheat off of me, Chris, but it's not going to work this time.
Damn. All right. I got to come up with another method. So building that bridge between domains, the data science space, and then the other spaces is very valuable. Sometimes if we are siloed in our own data science space, this concept of being more complicated, using the newest algorithm in vogue, the more complicated algorithm also is another pet peeve of mine. I've seen people building the most complicated neural networks using XGBoost and ensembling a million different models together, when sometimes a simple k-means would work, or sometimes a simple linear regression would work.
Well, first of all, XGBoost is amazing, so don't say anything bad about that. But I do agree with you generally that there's this need, I think, among data scientists to be at the cutting edge of algorithms and the newest thing. And whether or not that actually makes sense for what you're trying to do is not so much of a question. And it's funny because I just defended XGBoost, but so many of the times when I've done a model where I think like, oh, I'm going to need a neural network or I'm going to need all these other crazy things, the random forest just takes care of it. And there really is no need for us to go deep into the weeds of fine-tuning my like GBM model, right? And so like, it's very easy for us to just sit here and spew out new concepts and new models and this and that, but then not really need them and actually know how to use them in the right way.
And maybe it's just my own kind of preference here, but what I do instead of just turning to the most complex model first is I actually go for the easy models initially. And I think there's a lot of value to be gleaned from these more parsimonious models where you can really interpret the results and maybe look at coefficients and understand a change in this variable is associated with a change in that variable. All too often, you can't do that with these complicated models and you lose out. So maybe your accuracy is higher or whatever metric you're evaluating is higher and you know, you're predicting much better, but you really have no idea what's going on. And that's a pet peeve of mine.
Yeah, no, that's a great pet peeve, especially when you think about how for variable importance or even feature selection, we're oftentimes using other machine learning algorithms to help us make those decisions to then feed into the next set of machine learning algorithms. So it's very easy for us to say, okay, I'm just going to ignore the logistic regression or whatever. But there are actual insights that you can derive from that to make a better model down the line, instead of just jumping to the most complex, the newest, the craziest thing right away.
And, to be just a little bit of the devil's advocate here, for everything we kind of talked about today, I don't think most people do all these pet peeves intentionally or oftentimes for a reason where they're trying to obfuscate things or hide things. More often than not, I think it just happens and it's a misconception of what they're doing rather than this evil kind of persona.
I don't think anyone's doing it out of a need to be like intentionally vague. I think what's happening is that everyone wants to be in vogue. And so they're trying to be at the top. They're trying to be at the newest level. And it's it's unnecessary and it causes further complications. Today's pioneer is Raj Reddy, who is an Indian-American computer scientist and winner of the Turing Award. He's really well known for his contributions to a lot of different elements of machine learning, but especially speech recognition technology and the baseline systems that have been used to develop modern commercial speech recognition applications.
That's all we've got today in the world of banana data. We'll be back with another podcast in 2 weeks. But subscribe to the Banana Data newsletter to read these articles and more like them. And we've got links for all the articles we discussed today in the show notes below. Until next time.